In section 3.4, we were looking at box plots, and those box plots were giving us these quartiles that was separating our data into chunks of 25%. So that leads us into this next section where we're going to look a little more specifically at measures of relative standing. So instead of being concerned with the exact value that we have for an observation, we're interested in how that value compares to the rest of the distribution. So you might think after you take an exam how your score compares to the scores of others. Were you above or below the mean, and by how much? Maybe you want to know if you were in the top 5% of the class or among the top 25% of the class. So in order to answer these questions, we need to have this idea of relative standing. So there's two types of relative standing that we're going to look at, and the first one is the z-score. So a z-score is basically just telling you how many standard deviations from the mean your observation is. So you would take a particular data value and subtract the mean. That's going to give you the difference between the data value and the mean. Then you divide by the standard deviation, which will then provide you with the number of standard deviations the value is from the mean. A positive z-score means that it is that number of standard deviations above the mean, and a negative z-score simply means that you're that many observations below the mean. Sometimes you'll see these as standardized or standard scores. Here we can look at the mean and standard deviation for job offers based on different majors. An accounting major has a mean of $56,000 for a starting salary with a standard deviation of 1,500. Marketing has a mean of 52,500 for those offers with a standard deviation of 1,000. So if you have two students, one an accounting major and one a marketing major, how do we compare these two offers? Now, of course, we could always simply say that the accounting major had an offer that was $2,000 more than the marketing student, and that would absolutely be appropriate. But what would make even more sense here is to see how that offer compares to what is typical for observations in that particular distribution. So we'll take the accounting value, which that offer was $55,000, subtract the mean for accounting majors, and divide by the standard deviation of accounting majors. So that z-score is actually negative 0.67, telling us that the $55,000 salary is actually 0.67 standard deviations below the mean. The marketing student with a $53,000 offer, when we calculate that z-score by taking 53,000 minus 52,500, then dividing by the standard deviation and getting 0.5, that is actually 0.5 standard deviations above the mean. So relative to their distributions, the marketing offer is actually better than the accounting offer. But that's by comparing to the distribution that those values came from. One note on calculating these, you will need to use a calculator for these problems. I highly suggest doing the subtraction first, getting a value, and then doing the division. Most calculators will have a little bit of trouble with understanding what to subtract and what to divide. So if you'll do that in 2 steps, you're more likely to get the correct answer. Now, a note about z-scores is most of our z-scores from a mound-shaped and approximately symmetric distribution is going to fall within 2 standard deviations of the mean. So your z-scores should be between -2 and 2 for about 95% of the cases. 5% will be beyond that. If you go out 3 standard deviations, so z-scores between -3 and 3, you're going to capture about 99.7% of the observations. Only 0.3% of the observations will be even further away from that. So you can kind of think of z-scores less than -2 or greater than +2 would be among the smallest or largest values in a particular data set. We can formalize this idea with the empirical rule. And the empirical rule is a way for us to quantify what percentage of observations should fall within particular z-scores. 68% of the observations are going to be within 1 standard deviation of the mean. That means the z-scores will be between -1 and 1. Approximately 95% of the observations are going to be between 2 standard deviations from the mean. Z-scores would be between -2 and 2. And approximately 99.7% of the observations are within 3 standard deviations of the mean, so that would be z-scores between -3 and 3. This only applies when you have a mound-shaped with a single peak that's approximately symmetric for your distribution. Another way that we can express the empirical rule is graphically. Since 68% of the observations should fall within 1 standard deviation of the mean, we can think of that as 34% below and 34% above within that 1 standard deviation. To go from 68% to 95%, that's adding an additional 27% to our number. Well, if we split that, that's 13.5% of the values are going to be between 1 and 2 standard deviations. And then to get up to 99.7, we need to add an additional 2.35% on each side. So that tells us that between 2 and 3 standard deviations on either side, we should see 2.35% of the observations. Taking a look at an example, we can consider one of the earliest articles to promote using a distribution called the normal distribution, which is that picture that you just saw. One of the data sets in this article contained 1,052 measurements of the heights of mothers. The mean was 62.48 inches, the standard deviation was 2.39 inches. We were told that the distribution was mound-shaped and approximately symmetric. What we can derive from this is that we should have had about 68% of the observations 1 standard deviation from the mean. So if you take the mean and you subtract 1 standard deviation, and then you add 1 standard deviation, you're looking at the interval 60.094 to 64.874. We expect 68% of the observations to be there, when in fact in this actual data set we had 72.1, but that was pretty close. When we go to 2 standard deviations, we would expect about 95% of the observations to be in that range. So here we start with the mean and we subtract the standard deviation twice to get that lower value 57.704 and add the standard deviation twice to get 67.264. While we expect 95% from that empirical rule, we actually saw 96.2, but again that was pretty close to what we expected. Finally, to get the 99.7 interval, we need to subtract the standard deviation 3 times and add the standard deviation 3 times. So between 55.314 and 69.654, we expected to see 99.7% of the distribution. We actually saw 99.2, but we got very close with what we expected to see.